So welcome to the day 3 of the 2 questions of physics per day series. So here we are going to solve 2 questions again, question number 5 and question number 6. So question number 5 says that an electron microscope operates with a beam of electron, each of which has an energy 60 kilo electron volt. What is the smallest size that such a device could resolve? What must be the energy of such neutron in a beam of neutrons to be in order to resolve the same size of the object? Okay, so this question is asking for the smallest resolvable feature by an electron microscope which has the kinetic energy of 60 electron volt. Okay, and then we are required to find that if the same has to be resolved by the neutron, then what should be its energy? Okay, so we are going to use the de Broglie wavelength, minimum resolvable size, and something like that. Let us see how. So we know that the 60 kilo electron volt is very less than the electron's rest mass energy, which is 511 kilo electron volt. So this is going to be non-relativistic case, and we are going to find non-relativistic momentum, which is given by 2m kinetic energy whole under root. So when we put all the values, we are going to get 247 0.6 kilo electron volt per c. Okay, so how did we arrive at this? Let me tell you very clearly that momentum is 2 times mass times kinetic energy whole under root. But if you multiply the numerator by ca square, like 2m ca square, then k, and then divide by same. So here 2m ca square is nothing but rest mass energy. So we could write that 2 e naught k by c is the momentum. So this will provide you the easy to use easy to do mathematical computation, because we know that e naught for the electron is nothing but 511 kilo electron volt, and this is 60 kilo electron volt, and this is 2 here and divided by c. So upper value is now a lot easier to calculate, because you are simply getting 2 times 511 times 60 whole under root kev per c. Okay, so that is why this is a small mathematical manipulation which we all do to have the faster mathematical calculation, and this whole under root term is going to give you 247.6 kilo electron volt. And then when you have the momentum, then you can find the corresponding de Broglie wavelength, which is given by this. Okay, so smallest resolvable size is approximately of the same order of the wavelength. We know that, you should know that the smallest resolvable size is same as wavelength. Okay, so that means it is going to be 5.01 picometer. Now let us calculate the similar thing for neutron as well. So suppose neutron has to resolve the object of same size, so its lambda has to be same. Okay, its lambda has to be same, and once we get the all the required value, we can get the corresponding kinetic energy as well. So we require a neutron with same de Broglie wavelength, which is lambda equals to 5.01 picometer. Then we are going to find the momentum, and from the momentum we are going to find the kinetic energy. Okay, so these all are the values which we are going to use, and this is the corresponding kinetic energy. Okay, and in electron volt it is 32.6 electron volt. So the conclusion says that the smallest size resolvable by an electron microscope using 60 kilo electron volt is approximately 5.01 picometer. To achieve the same resolution using the neutrons, each neutron must have energy of approximately 32.6 electron volt. This demonstrates that electrons, being much lighter than electron, require significantly higher energies to achieve the same de Broglie wavelength and thus the same resolution capability. Now let us solve the question number 6, which says that for a particle of mass m, Schrodinger initially arrived at the wave equation given by this expression. You are required to show that a plane wave resolution of this equation is consistent with the relativistic energy momentum relationship. So relativistic energy momentum relationship is nothing but E square is equal to P square C square plus M square C to the power 4. Okay, if you think carefully, this is nothing but the square of the rest mass energy. Okay, because rest mass energy is mc square. So solution that we are going to assume a plane wave of this form, which is exponential minus iota kx minus omega t, where k is the propagation vector, k is propagation vector, and then omega is obviously the angular velocity, and this whole thing is phase, and so on. Okay, so what we are going to do, we know that this is the equation. In this particular equation, there is double derivative of wave equation with respect to time, and then there is single double derivative of the wave equation with respect to position. So we are going to find both. So double derivative of wave function with respect to time is minus omega square psi, and double derivative of wave function with respect to x is minus k square psi. You are going to calculate it yourself. It is very simple. Okay. Now these two values we are going to substitute it in the given expression of the wave equation of the Schrodinger, and which will lead us to this expression when we divide it by psi, because we know that in this whole equation we could divide LHS and RHS using the LHS and RHS by psi, which is wave function. So we get that it is minus omega square by c square equals to minus k square and minus m square c square h bar square. Now we know that energy is nothing but h bar omega. In that way, omega is nothing but E upon h bar. So we have substituted the same here, and the same thing we are going to substitute it for the k as well. Okay, so it is p square upon h square, and when we simplify it, we are going to get E square equals to p square c square plus m square c to the power 4. So that means we could say that this initially arrived wave equation by Schrodinger is consistent with the relativistic energy momentum relationship. That's it. And here you can write the small conclusion that the plane wave solution satisfies the given wave equation if and only if the dispersion relation is consistent with the relativistic energy momentum relationship. This confirms the internal consistency of the wave equation with the relativistic principles.